Somewhere right now, there's a version of you finishing listening to this same sentence at the same moment as you. Same thought, same hesitation, the same split second of doubt about whether this is fiction or real physics. It's physics, not just a version that resembles you, not a metaphor about potential or unlived choices, a physical copy made of the same atoms arranged in the same way, existing at this very moment somewhere in space that no telescope will ever reach. The explanation starts in a place that seems harmless, the size of the universe. The observable universe, the bubble of space whose light has had time to reach us since the Big Bang, is about 93 billion light years in diameter. The universe itself is 13.8 billion years old. The numbers may not add up at first, and it's not a mistake. Space stretched while the light was traveling, like a letter written on a rubber band that someone kept stretching throughout the delivery. But this 93 billion light-year bubble isn't the end of the universe. It's the end of our view from here. Beyond the edge, space almost certainly continues. The question that matters is, how far? Here comes a fact that few people have heard, but it changes everything. We know how to measure the curvature of space. It's not a metaphor. Space itself can be curved, just like the surface of a sphere is curved. If you draw a triangle on the surface of the Earth using great circle arcs, the internal angles add up to more than 180 degrees. In a space with negative curvature, like a horse saddle, they add up to less. The Planck satellite from the European Space Agency measured this curvature by observing the cosmic microwave background, the thermal echo of the universe, when the universe was 380,000 years old. And the result, with a margin of error of less than 0.5%, was flat. A flat universe, which doesn't fold in on itself like a cosmic donut, has no boundary. It just goes on, probably forever. To get a sense of how much is already there, just in the part we can observe, estimates range from 200 billion to 2 trillion galaxies each, with on average something close to 100 billion stars. The carbon in your body was forged inside a star that died before the sun was born. The iron in your blood came from a supernova so violent that for a few days it shone brighter than the entire galaxy in which it exploded. And that's just what we can already count within the 93 billion light-year bubble. Beyond the edge, by the reasoning you're about to hear, counting stops making sense. And this is where arithmetic gets uncomfortable. Your body, the planet, the entire galaxy around you. All of that is a specific configuration of matter, complex but finite. There are about 10 to the power of 10 to the 8th atoms in the observable universe. An absurdly large number, but countable in principle. A finite amount of particles can only arrange themselves in a finite number of ways. Take that finite number of possible arrangements, throw it into infinite space, distribute matter more or less uniformly, which is exactly what we observe in any direction we point a telescope. What happens? Think of a coin. If you flip it once, it can land heads or tails. If you flip it 1,000,000 times, both results will come up many times. If you flip it infinitely many times, every possible result, without exception, happens infinitely many times. It's not luck. It's a mathematical inevitability. Swap heads or tails for an arrangement of atoms the size of your observable universe. In an infinite space with uniform physics, every finite configuration of matter that can exist does exist. Not just once, infinitely many times. That includes you. There's not just one version of you. The physicist Max Tegmark, in a 2003 Scientific American article that later became the basis for the modern classification of multiverses, calculated the distance to the nearest copy of you, not of the entire planet, just of you, at something on the order of 10 raised to 10 raised to 29 meters. If you want an identical copy of the entire observable universe, from your neighborhood to the most distant quasar, the distance goes up to something close to 10 raised to 10 raised to 115 meters, according to the most recent calculations by Tegmark himself, now as a physicist at MIT. These are numbers that no human intuition can grasp. The entire observable universe, with its 93 billion light-years, is insignificant compared to these distances. But, and this but matters in a truly infinite space, distance is not an obstacle. It's just a number. The copy exists. It's just too far away for any light to ever reach. There is another version of you. She will never know that you exist. You will never know that she exists. And yet she is just as real as you are. The obvious objection is, how do we know that matter continues beyond the horizon? Maybe our observable bubble is a rare island of complexity surrounded by emptiness. That's a fair objection. Honestly, you can't check it directly. Checking would require seeing beyond what light allows. What supports the extrapolation is the so-called cosmological principle. On scales above 300 million light-years, the observed universe appears homogeneous and isotropic. The same density of galaxies, the same filaments and cosmic voids in any direction you point the telescope. It's not proof of what's beyond the horizon. It's the best extrapolation physics has, supported by everything we've measured so far. If it's correct, the same physics that produced you here keeps producing the same possibilities out there, including you again. There's a second layer to this story, and it comes from a period that lasted less than a billionth of a second. In 1981, the physicist Alan Guth proposed that in a fraction of an instant after the Big Bang, around 10 to the minus 32 seconds, the universe went through an exponential expansion. It doubled in size repeatedly at a speed that no clock will ever measure again, growing by a factor of at least 10 to the 26th power. This period, called cosmic inflation, explains why the universe is so flat, why the cosmic microwave background radiation is so uniform, and why certain exotic remnants predicted by particle physics have never been found. The strange detail is that once inflation starts, it's hard to stop it completely. Quantum fluctuations cause inflation to end in some regions, and it turns into a local Big Bang, its own bubble universe. While in other regions it continues, creating new Big Bangs nonstop. It's called eternal inflation, and it's the standard prediction of practically every inflationary model that cosmologists have tested to this day. The universe you're in, with its 93 billion light-years of observable space, would be just one bubble among a possibly infinite number of other bubbles, each one with its own Big Bang. Each one possibly with physical constants different from ours. In string theory, it is estimated that there are something like 10 to the 500 possible configurations for these physical laws. The so-called string landscape. Most of these configurations probably don't allow for chemistry or stars or anything resembling life. You only observe a universe compatible with your own existence, because logically you couldn't observe any other. This isn't mysticism, it's called the anthropic principle. And it explains, without needing any fine-tuning or intentional adjustment, why the constants we measure seem so convenient for our existence. Even among the bubbles that have physics similar to ours, and if eternal inflation is correct, there are infinitely many. Each one would again be internally infinite, and each one would have its own copies of you. This doesn't have to remain forever in the realm of pure speculation. If two inflationary bubbles have already collided in a relatively recent cosmic past, The collision may have left a mark on the cosmic background radiation, a subtle ring of temperature or polarization slightly different from the rest of the sky. Cosmologists have already looked for this pattern. Nothing conclusive has appeared yet. The next generation of instruments like CMBS-4 and the Simons Observatory and the future space mission LISA plan to detect gravitational waves coming from before light itself existed should really tighten this search in the next decade. It's not faith. It's an ongoing research program. Up to this point, everything depended on the universe being physically enormous. Now comes the part that doesn't depend on that, and for most theoretical physicists is the most solid of the four. Quantum mechanics is the most well-tested theory in the history of science, confirmed to a precision of about 1 part in a trillion in some experiments. And it describes reality not as a defined state, but as a superposition of possibilities, a wave function that assigns probabilities to each possible outcome of a measurement. The problem is that when you measure, you only see a result. The question that has haunted physics for decades was, what happens to the other possibilities? Richard Feynman, back in the 1940s, had already given a clue without realizing its significance. He reformulated quantum mechanics as a sum over histories. To calculate the chance of a particle going from one point to another, you sum the contribution of all possible paths it could have taken, not just the obvious path. His mathematics never claimed that these paths physically exist at the same time. But the idea that the correct calculation requires taking all possibilities seriously and not discarding the ones we didn't choose is the same intuition that reappears decades later in a very literal way. In 1957, a PhD student named Hugh Everett, supervised by John Wheeler at Princeton, he proposed an answer that, at the time, was practically ignored and today is taken seriously by a large part of the theoretical physics community. Nothing collapses. The wave function never chooses. It branches. Every time a quantum system interacts with anything capable of distinguishing between possible states, what's happening now? In every cubic centimeter of your body, reality splits into branches that stop interacting with each other. All the outcomes happen, just in different branches. Your brain is made of atoms. Atoms participate in quantum events all the time. This means that, in Everett's interpretation, there is right now a version of you who made a slightly different decision this morning. One who is still sleeping. One who never started listening to this. All of them as real as you. Each one feeling, from within its own branch, that it is the only real version that exists. You will never notice the branching. It is instantaneous and definitive. The process that physicists call decoherence ensures that, as soon as the branches separate, they become opaque to each other. From the inside, it just feels like one life, continuous, unique. From the outside, if there even is an outside, all the branches are equally real. Every atom in your body was something else before it became you. Every decision you make has already been, in another branch, a different decision. That raises a question that physics alone can't answer. Is that copy you, or is it just identical to you? The philosopher Derek Parfit spent much of his career on this question, and his conclusion, published in the book Reasons and Persons in 1984, was unsettling. According to him, the continuous personal identity we feel, the sense of being the same person we were 10 years ago, is not a deep metaphysical fact. It's a useful narrative that the brain constructs. Your body has changed almost completely since then. Your memories are imperfect reconstructions, rewritten every time you remember them. What remains is not a fixed essence, it's a pattern persisting through time. Parfit used a thought experiment that illustrates this well. Imagine a teleporter that scans every atom of your body destroys the original, and assembles a perfect copy somewhere else with the same memories and the same personality. Is the person who comes out on the other side you, or is it a copy that thinks it's you? Most people feel that something is lost in this process. But when you try to explain exactly what, the answer slips away. Your body has already replaced almost all the atoms it had a decade ago, and yet you don't feel like you've died in the meantime. It's the same question that the ancient Greeks asked about the ship of Theseus. If you replace each plank, one at a time, at what point does it stop being the same ship? Maybe the answer is that there was never a fixed ship to begin with. Just a pattern repeating its shape through ever-changing matter. If every possible choice branches out and happens somewhere, the natural question is, so does my decision matter?
It matters. Reason.
Simple. Even if all the outcomes happen in some branch, you, the specific version making this choice now, will only experience the consequences of the branch your decision creates. The version of you that chose carefully experiences the result of having chosen carefully. The version that chose in a hurry experiences the opposite. None of these versions observes the others. Each one lives entirely within the outcome of its own choice. Your effort doesn't decide whether a good outcome exists somewhere in the multiverse. It decides which branch you, specifically, will inhabit. There's even an indirect clue about this coming from the latest technology. Quantum computers, which have already moved beyond the drawing board and now run in laboratories at companies like Google and IBM, work precisely by exploiting superposition and entanglement, the same ingredients that support Everett's interpretation. They don't prove many worlds, but the fact that engineering works by treating multiple possibilities as simultaneously real and not as a mere calculational convenience is the kind of clue that keeps people taking the interpretation seriously by people who have no reason to defend a beautiful idea just because it's beautiful. There is an even stranger implication that most popular videos about the multiverse avoid mentioning because it is genuinely disturbing. In the 19th century, the physicist Ludwig Boltzmann showed that entropy, the measure of a system's disorder, is ultimately a matter of probability. Disordered states are more likely simply because there are many more ways for a system to be disordered than to be organized. In an infinite universe over a sufficiently long period of time, random thermal fluctuations can, in principle, assemble any organized structure purely by chance, including, in theory, a functional brain with false memories of an entire lifetime, existing for a fraction of a second before falling apart again. Cosmologists call this a Boltzmann brain. And the reason they take it seriously is statistical. In certain cosmological models, these random brains would outnumber the brains that actually evolved. If a model predicts that, most physicists consider it evidence against the model. Because you are in a low-entropy, coherent universe, the kind that a random fluctuation would hardly produce on its own. Even so, the fact that the question needs to be asked shows how far the logic of infinity can go. This counts as a technical problem that cosmology still hasn't properly solved, called the measure problem. If there are infinite versions of you spread across infinite space, or infinite quantum branches multiplying at every moment, comparing how many versions made one choice and how many made another is no longer a simple calculation. Infinity divided by infinity doesn't have a single answer. It depends on how you organize the counting. This doesn't invalidate the underlying argument, but it limits how much you can turn it into a precisely testable prediction. It's a real mathematical obstacle, not vague philosophy, and it's among the most discussed problems at the frontier of theoretical cosmology today. There is a fourth layer, even more speculative, which Tegmark himself advocates: the mathematical universe hypothesis. The idea is that every consistent mathematical structure exists physically, not as a description of reality, but as reality itself. Our universe wouldn't be special. It would just be one among infinite possible mathematical structures, and we happen to be in this one because it's one of the few that allows for consciousness. Not every physicist buys into this whole ladder. In 2014, cosmologists George Ellis and Joe Silk published an article in Nature magazine arguing that accepting multiverses without any form of observable confirmation risks turning physics into metaphysics disguised as science. On the other hand, physicists like Tegmark himself, David Deutsch, and Brian Greene argue that these ideas naturally emerge from the best theories we have: inflation, quantum mechanics, string theory, and that rejecting their conclusions just because they are uncomfortable is not scientific rigor. It's comfort disguised as rigor. Neither side is being irrational. It's a genuine debate at the top of theoretical physics with no resolution yet. What we can say with confidence is this: the universe is flat, gigantic, almost certainly bigger than anything we will ever be able to observe. Quantum mechanics is real and tested. The rest, eternal inflation, string landscape, many worlds as the correct interpretation. The mathematical universe ranges from robust predictions of already confirmed theories to the most coherent, speculative hypothesis. Honesty requires separating these categories, even when the conclusion of each one points to more versions of you. There's something curious about all this. Centuries before any satellite measured the curvature of space, philosophical traditions in completely different places came close to a similar intuition by other means. The Buddhist concept of anatta, often translated as non-self, does not deny that you exist. It denies that there is a fixed and continuous essence or nature behind experience. What exists in this view is process, a pattern being maintained, not a substance frozen in time. The Stoics came close to this from another angle, suggesting that clinging to the idea of a unique and unchanging self is a source of suffering, because this self was never as solid as it seemed. Physics doesn't prove philosophy, and it would be dishonest to say that it does. But when such different paths, equations on one side, meditation and logic on the other, centuries apart, come close to the same idea, it's at least worth stopping and taking notice. Maybe the right question isn't, is there another version of me? Maybe it's, what am I after all if I'm not a single thing? The answer that physics suggests is a pattern, a specific, temporary, extraordinarily complex arrangement of matter and information that processes the world around it and produces the experience of being here, now, listening to this. A pattern that might repeat somewhere too far to reach, or that might branch out right now inside your own skull. And I started looking at the night sky differently after fully understanding this argument. I no longer see just distant points of light. I see distance itself, the exact measure that separates you from yourself, so vast that even the word far can't describe it. That doesn't make you any less real. It makes reality bigger. It's not one version of you being real and the others being cheap copies. It's you being one instance among instances, each one complete, each one living the only life it can see from the inside. There isn't just one version of you. There never was. Somewhere, too far to reach, a copy of you is having this exact same thought right now. In some branch that split from yours just seconds ago, another version of you is feeling something slightly different from what you feel. None of them is more real than any of the others. None of them is exactly you. And at the same time, all of them are. And yet this one here, the one who is hearing this sentence right now, in this specific branch of whatever reality is, is the only life you will ever get to live.